The second lecture, we will complete whatever need for independence uh, from here on, which is enough. So, in the first lecture, we proved that if this is an independent random variables, then the joint distribution is product of the marginal distribution. That is necessarily our independent RVs, our independent RVs. Then P compose X inverse. This measure is nothing but the product measure. So we can apply Fubini to calculate the expectation, provided while using Fubini, we need to assume that either they are positive random variables or they are integrable. So we will just use the integrable one. So in order to keep things general, so the first lemma is if EXI mod xi are finite, then E product xi, since what we are using is necessarily the product measure, this is expectation of product xi. This is not absolutely apparent from Fubini's theorem. The proof follows directly from another more general lemma, which is if H, B, and R2 to R Borel function, such that expectation E, expectation H x comma y is finite. Yeah, expectation E H comma x is finite. Then expectation H x comma y. So so in our case, so we will not deal much with random variables which do not have a PDF, although there are certainly cases like that. And fx and fy are PDFs of x and y. Then expectation of h x comma y is equal to integral over R2 h x comma y d so fx dx fy dy and dx dy. Okay, the proof is simple. The proof necessarily it's enough to prove for simple functions, and then then we'll extend them. The proof. So I will just prove one statement in this proof, that if take one indicator 1a cross b, where a comma b belongs to Borel R, and lambda a comma lambda b are finite. So first assume h is a non-negative random variable. In that case, we do not even need finite. So because Fubini's theorem holds Fubini also holds for non-negative random variables. It does not require expectation finite, but however, we will use that here. So then the first step is to prove expectation 1a cross b, which is nothing but lambda 2a cross b. And in this definition, using the right hand side, we get this is lambda 1a, lambda 1b. And from properties of Lebesgue measure, we know that these two are equal. Then we can extend it to from correct integrator function to simple functions by linearity. Then by monotone convergence theorem, we can extend it to yeah. So by monotone convergence theorem, we can extend it to. So there is a little problem here. This right hand side is R2 integrator function A, integrator function B. This is not this. This is probability of x belongs to A, x belongs to B. This is not actually correct. Probability of x belongs to A, y belongs to B. And that is from P compose. This is this statement that I wrote is not correct. So this is P of x comma y. This is P of x belongs to A, y belongs to B. So this is P of x belongs to A by independence, P of y belongs to B. And by this is A, this is B, and this we know this is fx, fy dy, dx dy. So we are done. Now just use monotone convergence theorem. So we did it for the integrator functions. We can extend it to simple functions. First by linearity, from linearity by monotone convergence theorem, we can extend it to non-negative random variables. From non-negative random variables, and from there taking positive negative part, this lemma is proved. And applying this to the function product of excise, the initial lemma is proved, provided we check that yeah, so using that the lemma is proved, provided we check that it's enough that product of xi is finite if and only if the individual xi's expectation is finite. That is something we need to prove. It's tautological almost, so just check that. So yeah, so we get a very nice theorem. And now we will prove our most important results, that is proposition 1. If x has distribution f and y has distribution g, x and if x and y are independent, then x plus y has distribution z, x plus y equal to z, then z has distribution h, where h is nothing but the convolution of f and g, is nothing but convolution over r, f of z minus y, gy, dt. So essentially what we are doing is we are taking the class of all in the class of all L1 functions in R, the PDFs. So what this statement necessarily says is that an implication of this statements, we take the group of, we take all PDFs and on R, yeah, all PDFs on R, and we make this convolution operation. So this statement necessarily says that this is closed under the convolution operation. So that, and one can check that it won't be a group. It won't be a group because there will be no inverses, but it will form a semi-group under the convolution operation. So convolution of PDFs is again a PDF. That is what this statement says. And if x and y are independent, their sum has the distribution exactly the convolution. The proof is really straightforward. We need to show. So, so if x plus y is less than equal to z, we need to show this is integral minus infinity to z our h of z. The h of z we defined, h of z dz. h of, look at t dt maybe. Okay, this is not a very good notation. That is called this t and that to be z. So this is nothing but expectation indicator function minus infinity comma t x comma y. Sorry, this is nothing but indicator function. This is expectation of minus infinity comma t, not x plus y, of x plus y, which further can be written as indicator function of minus infinity, so comma t, h of x plus y, h of x comma y, where h is the function h of x comma y equal to x plus y. And using the basic property, this implies this is all such expectation of x plus y less than equal to t of x comma y. So, by the statement we proved a little while ago, this is over R2, integral over R2. Let's lead integral over R, 2R's, which is same as that by Fubini. This is expectation x plus y less than equal to t, h of x plus y. Let us write this. F of x, g of y, dy. Doing now indicator function of x plus y less than equal to t for a fixed y, because this is the product measure. This is nothing but indicator function x less than equal to t minus y. So this is integral over r expectation x comma y, x less than equal to t minus y, fx, this is one group, gy dx dy. This thing is nothing but indicator function x less than equal to t minus y, x. I may be wrong. Okay, so this thing is indicator function of x less than equal to t minus y of x. Yeah, this is so all such x into fx into gy dx dy. So what I mean to say is that yeah, that is there is some problem here. For a fixed x, these two functions coincide. Indicator function x plus y less than equal to t, x comma y. For a fixed y is same as indicator function of x, x less than equal to t minus 1. And this is nothing but, if we denote the joint CDF by this is nothing but f of t minus y gy dy. Yeah. Okay. But F of t minus y is not a CDF, but minus f comma y is a CDF. And one can check very easily just using that this has a PDF f of, so f of t minus y isn't a CDF, that's true, but for okay, for t it's a CDF. F of t minus y is a CDF for a fixed t is a CDF, and it has the PDF f of t minus y. I guess something is wrong. So g of t equal to ft minus y is a CDF, and this just give me a minute. So we get this expression up till now that this is integral over r ft minus y gy dy. But setting gt equal to ft minus y, this is still a CDF, and one can check that this CDF is nothing but f of z minus x minus infinity. This is exactly the CDF. Uh, minus z minus y dy. One can check this stuff. Think that this is exactly the CDF. This is not complicated. If this has f has CDF, this just integrate this, and assuming f is the CDF of f is the PDF of f capital F. So this statement, this star reduces to using Fubini and interchanging integrals, integral over minus infinity to t, integral over r f of z minus y gy dy. And hence this is our equation. Now notice one thing, we actually used here during the change of variable the invariance of the Lebesgue measure under the group operation. The Lebesgue measure is also very neatly invariant under some other group operations, that is product and division. So let us prove another theorem which will give a recipe to create more theorems later. So I am stating this without proof, and one can check this later by themselves. The I will give the recipe of the proof too. So proposition 2 is if x comma y are independent r.vs, and y is not equal to 0, then with PDFs f and g, then x by y has PDF h z, which is equal to integral over r y f z y gy. So these expressions look complicated, but one can generalize to locally compact groups of Haar measure with in random variables in that sense. So these are actually nothing but product in some weaker notion of Haar measures. PDFs product of PDFs is some weaker notion of Haar measures. So you can check this using the same recipe as before. That is, here the indicator function will be x by y less than equal to z, where x and y both, where y is non-negative, of course. So yeah. So using this recipe and following exactly above things, one can check that everything makes sense. So now we have a recipe to compute PDFs of sum of independent random variables. So although tedious and we won't do it now, if x and y are independent random variables are independent following normal distribution, suppose, so let us use this notation. Xi follows mu yi sigma I. Then using this recipe one can prove, using this, although the calculations are tedious, summation xi 1 to n follows normal summation mu I summation sigma I. We'll prove it in a different way later, and it will be a completely different proof using inversion formula and characteristic functions. But however, this gives a recipe. Also, if xi follows independent gamma, but the first may be ai, but the second, the variable needs to be fixed, then summation xi 1 to n follows gamma summation ai comma lambda. In particular, gamma 1 comma lambda is nothing but exponential lambda. Is nothing but exponential lambda. So one can check from this theorem that summation xi, if they follow, if xi's are IID exponential, then this is nothing but gamma n comma. Another, if x and y follow normal standard normal 0 1, they are IID. Then using our next result, proposition 2, one can show x by y follows Cauchy distribution, standard Cauchy standard. So we are given a recipe to calculate distribution, which sometimes may prove to be very tedious, and there are workarounds of it in specific cases. Now, before ending our discussion on random variables, a very important question exists. Now, we are talking about given distributions, independent random variables over it, but do they exist? Precisely, if if there is some distribution f and some distribution g, does there exist random variables that follow this and are independent? The question is true. The answer is true. And the proof is simple. Just take, so it's enough to prove from CDFs. So if F and G are CDFs, take the Lebesgue-Stieltjes measure, take lambda F product lambda 1. So if F and G are CDFs, take lambda F will be a probability measure, lambda Y will be a probability measure, the product will be a probability measure. Take lambda F and lambda Y, and the projection Pi, where I runs from 1 to 2, will actually be random variables with these distribution functions, and they will be independent. This is easy to check. So this is an exercise. And in fact, if this is something we won't prove but may use later, so this is the recipe, but this recipe is more difficult. If Fn are a sequence of random variables, sequence of CDFs, then, so that in that case, we will take an infinite product measure of probability measures. Then then on, so this thing lambda fi. So these needs to make sense. This is something called Kolmogorov extension theorem. The PIs so are independent, having CDFFI. So to conclude, if we mention that some random variables follow some distribution or independent IID, it makes sense. So because such random variables do exist.